Some of the biggest earthquakes that we know of occurred in 1947 at the locations of these yellow stars, and they were really strange. So their local magnitudes were much lower than their moment magnitude, and their local magnitudes only got up to about 5.9. They didn't produce much shaking at the coastline. People living in the town of Gisborne reported feeling a gentle ground rolling motion that went on for about a minute, but no really severe shaking. Despite being really quite insignificant earthquakes in terms of ground shaking, they were followed by up to 10-meter high tsunami. So events like these are really dangerous. They're really quite moderate earthquakes that produce anomalously large tsunami. So the earthquakes don't provide the ground shaking warning for people to evacuate to higher ground. So there's now about 20 years of GPS data in New Zealand that resolve the following picture of interseismic locking on the plate boundary fault. So the idea here is that the red colours show you places where the plate is locked and coupled, and presumably those are areas that are accumulating stress and will fail in a future earthquake. So rather worryingly, some of the strongest, deepest locking is beneath the capital city of Wellington here, where locking is strong down to depths of about 30 to 40 kilometres. Paleoseismology also suggests that this margin has experienced large magnitude 8 earthquakes in the past. And if this red patch ruptured, we would be able to get up to about a magnitude 8. So although there haven't been big earthquakes in the last 200 years, this margin seems to be capable of them. In the north, the story is completely different in that strong locking only exists down to depths of less than 10 kilometres. And most of the plate interface here is blue, and it's decoupled and presumably aseismically creeping. So we have really big differences between the north and the south. The GPS data is also revealed 2 types of slow slip events here. So in the south, we have these deep slow slip events at depths of about 30 to 50 kilometres. And these are similar to slow slip that's been found in places like Cascadia, and they're quite hard to study because they're so deep. It's the North Hikurangi margin that's caused all of the excitement and interest, because the slow slip events here in the dark green patches are really shallow, at depths of less than 2 kilometres to about 10 kilometres. It might be that these slow slip events actually go all the way to the seabed, but to resolve that we would have to drill some boreholes, put instruments in the boreholes to detect that slow slip. And that's one of the things that we have done in the last 8 to 18 months. Another reason why the Gisborne slow slip events are so interesting is that they happen really regularly like clockwork. So this is some GPS data from the Gisborne area, and you're looking at 4 different instruments at varying distances away from Gisborne. On the x-axis, we've got time from 2019 to 2013, and the y-axis kind of shows you the location of the GPS station. So when you've got these negative gentle gradients, that means that the GPS station is being pushed to the west. And that's what we'd expect to see during this interseismic locking phase when the overriding plate is being deformed. If we were to have an earthquake or a slow slip event, we would see things like this, where the GPS stations now move much more rapidly to the east. In the Gisborne data, although this movement looks quite rapid, it's actually taking place over about 4 weeks. So we're having the same fault slip as an up to moment magnitude 7 earthquake, but it's happening over a month. And as you can see from this data, those slow slip events happen every about 18 months to 2 years, to the point where we can almost predict when the next one's going to occur. And that's really cool because it means you don't have to leave your instruments down boreholes or on the seabed very long before you're pretty much guaranteed to detect the next slow slip event. So that's really exciting. The reason I am so interested in this area from an active source seismic reflection perspective is that these slow slip events are so shallow, we can image the faults where they occur on pretty bog standard seismic reflection profiles. So these white lines are seismic data that was collected prior to all of this new data collection. And they weren't really collected to learn about subduction zones, they were collected by the government and industry to look for oil and gas deposits along the margin. So they're really industry profiles. So the profile I'm going to show you comes from offshore the town of Gisborne, and it fortuitously runs right through the shallow slow slip patch and the source area of one of those 1947 tsunami earthquakes. So we can investigate both of those processes along this line. This is my favorite seismic reflection profile in the world. I think it's great. So it's 100 kilometers long, and it images down to depths of about 10 to 15 kilometers. This one is still in time. I will show you a depth migrated one a little bit later. The reason I love it so much, it's really nice to show students because it basically images a plate boundary, which is quite cool. So over here, we've got underformed sediments on the Pacific plate. And the fate of those sediments as the Pacific plate moves to the west is that when they reach the deformation front, they will end up being folded and faulted and deformed. The seabed rises here at the Turanganui Knoll seamount, and again, the fate of that seamount will eventually to become subducted down into the subduction system. This little triangular thing is the accretionary wedge that you've all seen in textbooks. This accretionary wedge is relatively small because the thickness of sediments is quite thin. It's only about 1 kilometre. What's important for us today is to note this very kind of high amplitude diagonal band, and this is the plate boundary fault itself. So this is the boundary between the Australian plate above and the Pacific plate below. The character of that fault is quite different in down dip. So in some places, like here, it's actually quite difficult to pick any reflection. We don't see very much at all, and that must mean that the acoustic impedance contrast, acoustic impedance being the product of density and p-wave velocity, is quite similar in the overriding and the downgoing plate. So the properties are quite similar. Interestingly, that's the area where the 1947 earthquake nucleated. I'm not going to say too much more about that in this talk, but if you're interested, then we can talk about that later. If we go down dip a bit more, we enter this area where the plate boundary is now defined by this kind of band of quite high amplitude continuous parallel reflections that has a thickness of about 1 kilometre. And this is the area where we've seen maximum cumulative slow slip since 2002. So it's quite tempting to think that whatever's responsible for those bright reflections could also in some way be behind why we get these shallow slow slip events here. So although seismic reflection data is great, it only goes so far. It shows us the geometries really nicely. We know that there must be some big acoustic impedance contrasts here, but we don't know exactly what's causing them. And we could come up with a number of hypotheses, and people have. So one suggestion has been that perhaps those bright reflections are due to the presence of fluids. Perhaps as the plate subducts, we have various dehydration reactions that produce water. Maybe if the overriding plate is impermeable, those fluids percolate up and then get ponded here, and perhaps we've got an area of high fluid pressure. That idea is somewhat supported by laboratory models that have tried to simulate slow slip events, and they often need high fluid pressure to reduce the effective stress to give you a propensity for slow slip rather than stick slip earthquake motion. An alternative hypothesis is perhaps what we're looking at is just a lithology that's quite variable. It's got very different velocities and densities, and it's giving us those bright reflections. We've always known that we've got these bright reflections kind of at the base of the incoming section, and until last year when we did the drilling, we didn't exactly know what those were. But maybe we're seeing the manifestation of that stuff when it gets subducted, and perhaps there's something a bit peculiar about those sediments that gives us slow slip. Laboratory models have also found that to get slow slip, you need conditionally stable frictional conditions, where the conditions are between velocity strengthening and velocity weakening. And one way to get that might be if you have a very mixed lithology with those different frictional properties. Maybe that's what we have down here. So back in 2011, we had an IODP workshop, and we started thinking about what hypotheses at Hikurangi we might be able to test with drilling. And we came up with a few key hypotheses. The first one was that slow slip doesn't stop at 2 kilometers beneath the seabed. It might go all the way to the seabed. The only way to really test that would be to drill some boreholes and put some instruments in there. So that's really a hypothesis we can only test with drilling. The second hypothesis is that perhaps in this area of high amplitude reflectivity where we have lots of slow slip, maybe the fluid pressure is high for the reasons I just explained. And the third hypothesis is that maybe this is an area where we have conditionally stable frictional conditions, perhaps due to variable lithologies, and that's why we have slow slip. So the most obvious way to test hypotheses 2 and 3 would be to drill down from the seabed into that area of high amplitude reflectivity. The problem with that is it's at a depth of about 4 to 5 kilometers. So if you've been following the Nantra-sized drilling that they've been doing in Nankai, they've been trying to penetrate the plate boundary at similar depths, and the project hasn't been successful. It hasn't been able to make it. It got to about 3.5 kilometers and couldn't go any deeper because the drilling conditions were just too difficult. We do have a proposal with the Chikyu facility board. That's a large ship that potentially could be capable of drilling down to these depths. But I think it's very unlikely that drilling's going to happen anytime soon, certainly not in the next 10 years, maybe even longer. So rather than shrug our shoulders and say, oh, we can't solve this issue, we've come up with another experiment, which rather than involving deep drilling, it involves a combination of new seismic data collection and shallow drilling. So the idea here is that we will collect some new seismic data, not geared up to produce pretty seismic reflection pictures, but more geared up to resolve what the velocity structure is of the margin at a high resolution. If hypothesis 2 is correct, we'd expect that high amplitude zone to also be a low velocity anomaly if it's got lots of fluids at high fluid pressure. So if we could resolve a seismic model that could let us see into that area, maybe we could test hypothesis 2. The problem with that would be that you could argue, even if we do find a low velocity anomaly, you could say, well, maybe it's just due to lithology. Maybe you've got a very low velocity lithology down there. But if we also had some shallow drilling through the incoming section, we could take some samples of these lithologies, experiment on them in the lab to see what velocity they would have at this depth and what velocity they'd have for different fluid pressures, and then we'd be able to diagnose from our velocity models exactly what's going on in that zone. So it probably won't surprise you to know that that's what we've done in the last 18 months. So we've collected the data optimally to get this high resolution velocity model, and we've done that shallow drilling. So in the first part of this talk, I'm going to talk to you about the seismic data collection, and then I'm going to move on to the drilling. Okay, this is my scariest geophysical slide. So the traditional way that people produce velocity models with active source seismic data is using a technique called travel time tomography. So what this involves is often collecting data not with a streamer hung behind a ship, but instead it involves the deployment of ocean bottom seismometers or nodes. The benefit of this is that it gives you greater offsets between your source and your receiver. To calculate velocities, the waves we're really interested in are the turning waves, which kind of travel through the area horizontally. We're not so interested in the vertical reflections. So what people do is they produce a starting velocity model, compute synthetic data through it, and compare the arrival time of the modeled data with the field data. If they match, as they do in this example, that suggests that your model is pretty good. This technique is good because it's fast and it's cheap. We've been doing it for years, but it's limited in terms of its spatial resolution. It's limited to the width of a Fresnel zone, which is related to the square root of the seismic wavelength times the target depth. So if I put some dummy numbers in here, if we're in an area where the P wave velocity is 3 kilometers per second, our source has a dominant frequency of 30 hertz, we're trying to image to 2 kilometers, we would have a I'm losing my voice. We would have a resolution in our velocity models of around 500 meters. And that might not be good enough to resolve what's going on in that slow slip zone. Fortunately, in the last few years, a new technique has become computationally feasible called 3D full waveform inversion with active source seismic data. This technique is different in that we're now not just trying to model the first arrival times, we're now trying to model the complete waveform, wiggle for wiggle and trace by trace. So we're now using much more of the data, not just those first arrivals. The benefit of this method is that theoretically we can now get up to a resolution of a wavelength over 2, and if I put those dummy numbers back in, that would give us a resolution of 50 meters, so it's improved by an order of magnitude. The problem with this method is that it's very computationally intensive. You have to do it on a supercomputer, and if you're doing 3D FWI, it can take weeks, months just to process one model. The technology is also not yet robust. It's still very much kind of evolving and developing. So there's a lot of work you need to do to quality control the model and check things are working well. I'm very fortunate at Imperial College to get to work with Mike Warner and Joe Morgan, and they've been developing 3D FWI codes to use with active source seismic data over the last 20 years, thanks to money from an oil and gas consortium. So their codes are now in use by many companies, and they've proven to be really good at finding gas reservoirs in areas where the stratigraphy is very simple, like the North Sea. What Mike and Joe are now keen to do is to try to translate this technology to solve really big tectonic problems like this one. And they've been trying to apply the technology at places like the Chicxulub impact crater in the Gulf of Mexico and also Santorini, the volcano in Greece. The example on the right, I think, just shows you the potential of this method. So in this diagram, we have some data collected across the Nankai subduction zone with OBS. And this is the velocity model produced with travel time tomography. You might not even have guessed this is a subduction zone. We don't even see the kind of downgoing plate. The same data here has been processed with 2D FWI using some quite old codes now. But this time we now see the downgoing plate as a low velocity zone. So a few years ago, we were really keen to apply this technology to Hikurangi to see if we could resolve what the velocity structure is in the slow slip zone in 3 dimensions. But before we could convince funders to give us the money to go and do that, we had to prove it would work in a place where the water depths are really variable and the structure is really complicated. So we did a pilot study, which was done by my PhD student, Melissa Gray, who's about to hand in her thesis this week. And this work was just published in JGR Solid Earth last week. So if you want to learn more about it, that's a good place to go. So this is the same seismic line that I've showed you before, my favorite one. This one has been pre-stack depth migrated, though, this time. So what we did is we took a starting velocity model that was produced with very conventional techniques, and it was produced by Dan Barker from GNS Science, where I used to work, when he did the pre-stack depth migration of this line. So as you can see, it's quite blobby. There we can see some hints of geological structure, like this looks like it might be a thrust fault. But there are areas where we can see features in the reflection data that aren't in the velocity model. For example, here, there's this nice little triangular volcanic cone, which just doesn't feature in the velocity model at all. It just cuts straight across it. Also, in this area, we've got this sin form, whereas in the starting velocity model, the velocities just cut straight through it. They don't kind of follow the stratigraphy like you might expect. So what Melissa did was apply Joe and Mike's FWI codes in 2D, because this is all the data we had. And I should say that the best data we had before we did this new data collection was collected with a 12-kilometer streamer. So as I mentioned before, to get good velocity models deep, you need long offsets between your source and your receiver. For FWI to work well, you really need the offset to be 6 times the target depth. So with a streamer of 12 kilometers, we can really only hope to get good imaging to about 2 kilometers. So with these data, we can't image the slow slip zone right now, but what we can do is investigate what the structure of the overriding plate is and what the incoming section is, and basically prove the concept. So we can hopefully convince funders to let us go and collect the 3D data. So this is what she found when she applied those 2D FWI codes. So I'll just kind of flick back and forth. So I'm flicking back and forth as if this is nothing, but to get from here to here actually took about 18 months of PhD time. So it's really time consuming. But I think you'll agree, there's an awful lot more detail that we can see here. The problem is, though, is all this detail real, or are these just artifacts? So to test this, we did 3 things. So the first thing we did was a kind of observational check. So we checked to see if there were any features popping out of the FWI model which we know exist in the reflection data, but we didn't see in the original velocity model. So that volcanic cone that I mentioned before has now popped out beautifully, which gives us confidence that this is actually doing something sensible. The other place was that synform that we saw before, and the FWI velocities are now beautifully kind of following it. There were a few very low velocity anomalies in here, which we were a bit skeptical about, but when we spoke to the gas hydrates team in New Zealand, they actually have some evidence of gas hydrates in that area, so actually some of those might be real as well. What it really beautifully picks out are some of the faults. So the frontal thrust you can see here, we've got the higher velocity in the hanging wall, which you'd expect because it's been over-compacted. But what's really of interest is that some of the faults, like the frontal thrust and some of these bigger faults back here, they are associated with these low velocity zones. So we're kind of tempted to suggest that that's related to the flow of fluids along these faults. Not all of the faults have this, so it looks like perhaps some of the faults are behaving as conduits for fluid, but not all of them. The second test is much more quantitative. So we've taken a shot gather at a single location, and here we're looking at the data collected on that 12-kilometer streamer. We've shown 10 traces of the real data, and you can tell what's the real data because it's got the noise up here in the water column, and we've kind of interwoven them with 12 traces of the modeled data. So if the model is doing things right, you shouldn't see a gap, the line should be completely smooth. So in this diagram, you're seeing the real data compared with the modeled data through that starting velocity model. So at near offsets, the two match really nicely, that looks pretty good, but at far offsets, you can see that it's going up and down, the line's not continuous. The modeled data is coming in a bit too early. In this diagram, we now see the same thing, but now this is the synthetic data shot through the FWI model. So at far offsets, it's now much more continuous, and we're also seeing later arrivals showing up much more nicely too. So from this, we're pretty confident that the FWI is physically doing a much better job. The last thing we can do, because we have drilling data here now, we can actually compare the FWI model to logging while drilling logs that were acquired during the IODP expeditions. So the blue line that you see here is the VP log that was collected on Expedition 372 from this site, 15 and 19. The yellow line is through the original velocity model, and the purple line is through the FWI model. So the starting model was already pretty good, and that's what we need for FWI to work. FWI doesn't stop you kind of doing that initial velocity model building, it just improves things, it just kind of takes things to the next level. So this velocity gradient you can see in here is now much improved in this model. And we're beginning to get hints of that velocity inversion. The match isn't perfect, and we wouldn't expect it to be, because the FWI model is driven by the turning waves, which are really telling us about the horizontal velocity structure. The drilling data is obviously telling us about the vertical structure. So if there's any anisotropy, those two won't be the same. Now we've got the drilling data, we've got a bit of an idea of what the anisotropy might be like here, we can then try an anisotropic for waveform inversion, and we might be able to get that match even better. But anyway, this gave us confidence that it might be a good idea to go out and collect data optimally for full waveform inversion, not just to look at the shallow surface, but to look at that slow slip patch. So remember, to look at that slow slip patch, we need offsets of at least 60 kilometers to see down to 10 kilometers, ideally more like 100 kilometers. So the project, which we eventually got funded from various sources, this was really an international project, involved 3 different components. So the first component was an active source seismic reflection volume collected by the Marcus Langseth, and this project was led by Nathan Bangs from the UTIG. So in this box, we collected a 3D seismic reflection volume, which is in the process of being processed by Repsol. And when that data has finished being processed, it's going to pretty much almost immediately going to become publicly available. So you'll be able to take a look at that. The other component was that our Japanese colleagues from JAMSTEC brought 100 ocean bottom seismometers to put in the footprint of that 3D survey. This is good because when the ship is shooting over here, we've got a maximum offset of about 60 kilometers, which will enable us to get to the depths that we want. The slight problem with this offshore study is that the maximum cumulative slow slip kind of happens here, where the water depths are too deep to put the OBS or to have the shooting. So in the part of the project which I led, we deployed 200 seismometers onshore in this area. So the idea was when the ship is shooting out here, the waves will travel through the slow slip zone and then be detected by our onshore array. And we'll be able to image further west of the zone where we actually have the offshore instruments. So our array consisted of 50 broadband seismometers that you can see here. These are 6 TDs from SEIS UK. We deployed them about every 2 kilometers to be a similar spacing to the OBS network. For FWI to work well, you need very short station spacing. You need a very high density of instruments. So we're collecting data in quite an unusual way compared to how particularly passive seismic studies would usually run. The project was supposed to just be an active source project. We were basically going to put the instruments out. A month later, when the ship stopped, we would pull them all up again. But it turned out to be such a huge physical effort to get all 50 of these stations in that NERC gave us an extension from December until October. So actually we have a decent passive seismic record too. So we're now very interested to talk to passive seismologists about what kind of studies could be done with this new data set. As well as those broadbands, we also had 145 short period instruments, some of them from the Potsdam Geophysical Instrument Facility in Germany. These are much faster to deploy. And you can see we've put most of these concentrated in this area. The reason we did this is that during our scouting trip, we found that in this area, which is called the Waimata Valley, there was lots of evidence of active mud volcanism. So in Google Earth, you can still see the scars of previous mud volcanoes from the 1930s. And during our trip, we spoke to landowners in this area who said that every few weeks they were having to repair fences because the land was inflating so much. And we witnessed some kind of bubbling mud pools while we were there. So we thought with these extra seismometers it would be really exciting to put huge numbers, kind of spaced every 500 meters in this region. And that's what we did. The instruments were all pulled up in October, and in December I had an email from the landowners of this area, pretty much where the arrow is, to say that a big volcano eruption had happened, pretty much exactly where they kept fixing those fences. So we think we could potentially have a really exciting data set here to look at acoustic signals produced by mud diapirs as they rise through the subsurface, and that's something we'd like to kind of talk with other people that are more, have done more work on volcano seismology to see what could be done. We haven't really got our teeth stuck into the analysis yet. The data hasn't been collected that long. But one thing we have done is looked at a few of the local earthquakes. So this was an earthquake which happened 15 kilometers or so away from the array in January 2018. We have a huge amount of data, so we can really start to look at this in much more of a nodal type fashion. So what we've done here is picked the P wave first arrival, and I'm showing the time it takes the P wave to reach all of the instruments in our array. And what we've noticed from this earthquake, but also many others, is that there's this area, this patch up here, where the P wave speeds, the P waves are arriving a lot later than we would expect based on their distance. And this is exactly that area where we had the mud volcano and the bubbling. So we think we've got a really exciting data set here that shows you what's happening in the subsurface just before a mud volcano erupts. We pretty much did have a station here, but luckily it had been taken away before the volcano happened. Cool. So I'm going to transition here now to talk about the drilling data. So ECORD, as part of my lecture series, have asked me to say a few words about IODP, particularly for students who might not be so familiar with the program. So IODP is the International Ocean Discovery Program, and they're really the world's kind of largest research program. They're probably only second to the space program in terms of ambition. It involves 23 member countries, of which all of us in this room belong to ECORD. So ECORD are the European Consortium for Ocean Drilling, which involves 14 European countries and Canada. And this provides us with opportunities to submit proposals, to join other people's expeditions, and to join the workshops and summer schools that ECORD organise every year. IODP are really interested, and ECORD, to hear from early career scientists. So over the last year, we've had lots of workshops for PhD students to kind of teach you how to write an IODP proposal. We want to start to see more proposals coming in from early career people. IODP have a number of drilling platforms. The JOIDES Resolution is really their kind of key workhorse. This is a non-riser vessel, and it's capable of drilling to about 2 kilometers depth. That's pretty much about the kind of limit, at least in the water depths that we're dealing with at subduction zones. And that's operated by the US. The CHIKU is a much larger vessel operated by Japan. It's a riser vessel, which means it potentially should be able to drill to depths of about 5 kilometers in subduction zones, although at Nankai that's proving to be very challenging. ECORD are responsible for arranging mission-specific platforms. So these are basically vessels that you use when you can't use the other two, if the other two wouldn't work. So the types of projects that ECORD have run recently with mission-specific platforms is one which I was also involved in the Corinth Rift. This is where I did my PhD. So the idea here was to drill down to about 400 meters to date the stratigraphy, to look at subsidence and fault evolution. Sounds pretty simple. The problem here was the Corinth Canal was too narrow for the JOIDES Resolution to get in, and there's a bridge the other side of the Gulf which the derrick couldn't get through. So instead, ECORD had to hire a vessel from Fugro to do that drilling. Another expedition recently was the Chicxulub impact crater in the Gulf of Mexico. The water depths were too shallow there for a regular research drilling vessel, so they had to hire one of these rigs. So Expedition 372 and 375 aimed, as I mentioned earlier, to do this shallow drilling, which hopefully will one day complement deeper drilling into those high amplitude reflections. So in this project, which we did with the JOIDES resolution, we had a few objectives. The first thing we wanted to do, which I've already mentioned, is we wanted to drill into that incoming section to see what the lithologies are here. This is critical because the plate boundary is forming somewhere within this section, and it's likely that some of this is subducted in that region which has slow slip. We also wanted to see what the faults here look like. Were the faults very narrow? Were they very wide, more like sheer kind of deformation bands? What was their character? We can't get down to the plate boundary fault, so instead we drilled one of these large splay faults. And based on the seismic interpretation, we think this fault has a displacement of up to 6 kilometers. So it's a pretty big one. We also drilled above the slow slip patch, and both of these sites we put borehole observatories in called corks to detect slow slip and fluid pressure changes, fluid chemistry changes during the slow slip cycle. So at all of these sites, we wanted to core. We wanted to actually get samples that we could then experiment on in the laboratory. And at 3 of the sites, we collected logging while drilling data, and we deployed those 2 borehole observatories. So with all of these objectives, there was too much there to fit into a traditional 2-month drilling expedition. So that's as long as the drilling expeditions are. I think they've decided 2 months is enough for crew and scientists to be offshore before you start to go a bit mad. So that's kind of the maximum. So this had to be split into 2 expeditions. So the first expedition did the logging while drilling objectives. That was 372. And you can see them here celebrating 50 years of ocean drilling. And 375 went back out in March of 2018. You can see me there. And we did the coring objectives and the installation of those borehole observatories. So in the interest of time, I'm just going to talk to you about 2 of these sites. I'm going to start with 1518, which is through the fault zone, and then I'll move on to that incoming section. So this is the favourite of seismic line again, depth migrated, which shows you kind of the location of our drill sites. You can see why we drilled here. We've got this nice hanging wall anticline. You can kind of see, looks like a fault through here. The footwall stratigraphy, interestingly, is quite parallel to the fault, which is not necessarily what you'd expect. The FWI model, which we had after we did the drilling planning, so this kind of happened after, suggests that perhaps we won't expect to see very significant velocity changes in the fault zone. Some of the other faults, like the frontal thrust, seem to have this kind of low velocity channel along them, but this one doesn't seem to. So our interpretation from the FWI is perhaps some of these faults are conduits for fluid, but perhaps this one that we've drilled maybe is not. So this is what we found. So the lithologies of the hanging wall and the footwall were quite similar. The hanging wall consists of silty clay with some coarser grained silt beds and sand. Basically, we're dealing with turbidites here that have deposited in a hemipelagic setting. The structural geologists recorded that the bedding orientations are really variable. In some cases, they get really steep. In some cases, they're clearly overturned. And I think that's the reason why the seismic data here is quite acoustically transparent. This is our synthetic seismic tie, which we did with the velocity and density from the LWD, and it really doesn't match the data at all. And I think that's because the structure is so complicated, we're just not getting coherent reflections in the profile. The structural geologists also found lots of evidence of normal faulting in particular, as well as the faulting. It's a bit hard to see there. At 300 meters from the seismic data, we expected to encounter the fault, and we did. The fault turned out to be a highly deformed 18-meter thick zone with a significant age reversal. So this seems to be the most significant structure. There was a secondary fault a little bit deeper. The fault zone was interesting in that in some parts of that 18-meter, we saw lots of evidence of brittle deformation again. But in other areas, we saw ductile flow banding. So it seems that there's a bit of a kind of mixture of deformation modes in this fault zone, which I'll talk about on the next slide. Going into the hanging wall, the lithologies are very similar to the going to the footwall, the lithologies are very similar to the hanging wall, but we've got much more mass transport deposits and biotubation. And the bedding dips are much more consistent, as we can see from the seismic data too. In terms of porosity, the porosity gradually decreases with depth, as we'd expect, but at the fault zone, we don't really see much of an increase in porosity. It increases a little bit, but not really outside of the error bars. The big difference in porosity happens when you get from the fault to the footwall. The geochemists also didn't see any real evidence here for fluid flow or high fluid pressure. So as we thought from the FWI model, perhaps this isn't a fault which is acting as a conduit for fluid. Maybe any fluids kind of coming through here are instead percolating through the higher porosity footwall rather than the fault zone itself. The structural geologists on board, like Aki Fangareng, got very excited about the fault zone because of this mixture of deformation styles. So they found that some parts of the fault were clearly very brecciated, whereas others had this flow banding. So we don't know at the moment how this fault behaves. It might turn out that this fault undergoes slow slip. This fault is also potentially a candidate for the 1947 tsunami earthquake. The fact we found this mixture of deformation styles might provide us with a mechanism whereby we could get regular earthquakes here and perhaps at other times slow slip events. So the key thing we need to know now is, does this fault undergo slow slip? So to determine that, we've installed two of these borehole observatories, these corks that I mentioned. So this was a separate project funded by NSF, led by Laura Wallace. So this involves drilling a 400-meter deep hole through the fault and then dangling a series of instruments down that hole. This one was quite complicated. It involved 3 screens which had instrumentation on them, one in the footwall, one in the fault zone itself, and then one in the hanging wall. And these were measuring things like pore pressure, fluid flow rates, taking fluid geochemistry samples over time, and there's also a row of temperature sensors as well. These data are not being beamed back to us in real time, unfortunately. They're being stored in this data logger at the seabed, and this is what that data logger looked like before we sent it down. So you basically have to go back with a remotely operated vehicle, put in a USB stick to download the data. So when we deployed these, we basically just had to leave them and go, okay, we hope they're working. Laura Wallace and her team went back in February of this year, downloaded some data, and they are both working. The other cool thing is that in April this year, a big slow slip event happened. So I think we have captured a slow slip event with these instruments. The next time they get the data, that's going to be really exciting. Also, just a fun fact, this is now the tallest man-made feature in New Zealand. The tallest man-made feature was the Sky Tower in Auckland, and now it's our 400-meter long cork observatory. So another thing I'd like to show you at this point is just a quick video of some underwater camera footage to show the installation of that cork observatory. So we've got the drill string here, and this is the data logger on the end. Some of you might have seen the other thing in this video. It will loop round again. So if you keep an eye on the right-hand side of the picture, you'll see a squid, which despite having the entire ocean to swim in, has to slap straight back into our observatory. So I think this happened about midway through the cruise, and it really cheered us up that day. But I don't think that's the end of the story for this squid, and I will tell you my hypothesis of what I think happened to the squid at the end of this talk. Okay, so the last geoscience thing I'm going to talk about before we get back to the squid is site 1520, which is a really important site because it's going through that incoming section. And again, the fault is forming within here somewhere. Some of this material is going to be subducted. From the FWI model, which remember we had after we planned the drilling, we'd expected to see perhaps 3 different lithologies here. Down to about 500 meters, we've got fairly low velocities. It then kicks up. The seismic fasces character looks quite different here as well in the yellow. And then at 850, we go into this higher velocity material. The velocities, though, were only up to about 3 kilometers per second. So we kept getting asked, do you think we're going to hit ocean basement? And with the geophysicists were like, no, we think the velocities are too low. So this is what we found. This is probably the most exciting core in terms of for the sedimentologists. So down to about 500 meters, where we expected from the FWI model, we did have a change in lithology. It went from turbidites, very much like we saw at 1518, to pelagic sediments, these marls, calcareous mudstones, and chalks. And you can see them there, these grey and these buff-coloured sediments in here. There are also a few debris flows consisting of these kind of basalt clasts that look like they've rolled down the side of that seamount, remember we saw on the seismic reflection profile. At 850, we see this beautiful transition between pelagics and volcaniclastic sediments. And those volcaniclastic sediments we found pretty much down to the bottom of the hole at about 1 kilometre. The crew that were working when these sediments came up, got really excited because the core liner looked really black. So they were like, oh, we've drilled oceanic crust, the geophysicists were completely wrong. But when we split the cores, they actually turned out to be very rich organic mudstone. So we didn't hit basement at all, they were just these volcaniclastics. The volcaniclastics are also super interesting because their velocities are highly variable. So in some parts, the velocities get down to about 1.7 kilometers per second. It's almost as gooey as water. And then in other areas, when we took samples in the lab, the velocities got up to about 5 kilometers per second. So we've got a material which has wildly different velocities, very different elastic properties. So the rock mechanics people on the team are now taking samples of these rocks, exploring in the laboratory whether when these rocks get to those kind of depths as the slow slip zone, maybe they just spontaneously produce slow slip events. Maybe we don't need high fluid pressures at all. Maybe, again, it's to do with those variable lithologies, perhaps variable frictional conditions, why we have slow slip. So I don't have conclusions for you because this is very much ongoing. We've got loads of new data now and we're trying to hire lots of PhD students and postdocs to help us kind of work through it all. So just as a summary, kind of the story so far. So that first hypothesis, that slow slip events propagate to the trench, I think we will now know the answer to that in a year. Now we've had the slow slip event, the observatories have detected it. As long as the data gets collected okay, then we should be able to answer that, or Laura Wallace at least and her team will be able to answer that in the year. The second hypothesis about poor fluid pressure, the fault we drilled didn't show any evidence of overpressure, but we've now got this 3D seismic array which will hopefully let us resolve what the velocities are in that slow slip zone and test that one. The third hypothesis about conditional frictional stability and perhaps variable lithologies. The drilled fault zone was a mixture of brittle and ductile deformation, but we don't know yet whether that hosts slow slip. We should know that within the year, but the incoming section was certainly very heterogeneous. And we have a paper which I think hopefully is coming out in scientific reports soon on that by Barnes et al. All of the work we did on the ship is now published in this Proceedings of the IODP volume, which came out recently, and all of the drilling data is all completely public now as well, so you can go and take a look at that. Before I finish, I'd just like to share with you my hypothesis for the squid. So this video was taken 20 minutes after the other one that we watched. And if you watch in the right-hand corner, you can see a squid coming along. It's already got quite a lot of ink, it's a bit hard to see. And then this thing comes out with lots of arms. So when we first saw this, we thought it was an octopus attack. In fact, we labeled the file as that. But we tweeted this to the Monterey Bay Aquarium, and they think it's a case of squid on squid cannibalism. So that was an extra bit of science that we did. And on that note, I think I'll leave it there and happy to answer any questions. Thank you. Thank you.
On your favorite seismic profile, the place boundary is actually very, it looks like it's very flat, but to the left-hand side, it looks like it's
Kinks.
deep.
Yeah.
So I was wondering if this curvature was due to flexural bulges.
Yeah, so, I mean, so if you remember that one of the first slides I showed with the interseismic coupling map, there was that big transition. So when that was discovered, I think the first thought was like, oh, it's probably due to changes in the dip of the plate. So we kind of went back to all of our seismic profiles, mapped them all out to find out the geometry of the plate boundary. And what we found is that in the south, the plate boundary dips at about 5 degrees. And as you get up into this northern zone, as you've noticed, it is quite shallow, but then it begins to dip quite steeply, and it ends up getting to about 8 degrees. So there definitely is a difference in the angle of the plate boundary fault from north to south. But what we found is that the kind of transition was, it was relatively distinct, but it happened not at that transition with interseismic coupling, it happened quite a bit further north. So although there definitely are some changes in the dip angle of the plate here, it's not obviously connected with that change in interseismic coupling. But there are definitely some changes from north to south, and it is certainly steeper in the north. Something above it, yeah. So this area, as you can see from the data, is the imaging is really poor in this area, and this is an area where we hope the 3D seismic reflection volume is going to help us. What I didn't talk about, which probably is related to your question, is that you'll see these like slightly red dashed lines in here, and this is mapping out where we think there's a subducted seamount. So that change in dip angle is where we have a thing which is probably quite similar in size to the Hikurangi Knolls seamount, which is subducted. It's quite subtle from the seismic data. There is that change in plate geometry which somewhat supports it, but the big evidence we've got for that is the magnetic data. So there's a magnetic anomaly matches that area. But with the new 3D seismic, what we're hoping is that we'll get better imaging of this area, and what we expect is that if this is a seamount, we'll probably see vast amounts of faulting. Maybe that's why we don't image it very well, including some normal faults, in that this area is going to be kind of highly fractured. And with the 3D data, hopefully we can look at time slices and actually see the geometries of those fractures. So yeah, we do expect that area to be pretty deformed. We did see some normal faults in the drill site, but it's clearly related there with that hanging wall anticline and the kind of flexure above that. In there, I know the one you mean. Yeah. This one. Yes, yeah. So another thing we've been working on now is that now we've got this velocity model, we've got the drilling data, we've been trying to get relationships between velocity and porosity to basically calculate a porosity map. So what we find here is that as we go towards the trench, these sediments, the velocity does change, and it increases as you get about 10 kilometers away from the trench. So we think this is basically, highlighting the point at which it starts to feel the lateral compression of the subduction zone. So we're kind of capturing that. So I think some of these lateral velocity variations are real. Some of them, though, there are some weird anomalies in here. We could debate whether we think these are real. If Melissa was here, the PhD student who did it, she is pretty confident that when she does those shot gathers through here, she thinks that the kind of arrivals through these layers match much better in the FWI compared to the real. This area is pretty complicated in that we've got those pelagics that we saw in the drill site. I mean, the pelagics that we encountered here actually look like they're just a little, almost kind of debris flow. It doesn't look like a continuous unit. So again, it's kind of like, hindsight's a wonderful thing, but we wish that we'd actually taken this drill site a bit further over here, which looks a bit more representative of this incoming material. We wonder if we've captured something that's actually a little bit of an anomaly. But one of the problems we've got here is interpreting exactly where the boundary is between the pelagics and the volcaniclastics, tracing that to the deformation front. So at the moment, we can't be super confident exactly where the plate boundary is forming, whether it's in the pelagics, whether it's at the pelagics volcaniclastics boundary, or if it's within the volcaniclastics. Again, we're hoping the 3D data will help a bit, but it's not helped by some of these giant volcanic cones that I think might be, so long along strike, we might not actually be able to map round them, so we still kind of might have this issue. Sorry, which this? Oh, this is the seamount. So this is the Taranganui Knoll seamount. So we deliberately drilled here because we could get to those flank sediments at a shallower depth. That's why we didn't drill out there in the first place. So this is the Taranganui Knoll seamount. We also drilled a site about here, right on top. It was only about 40 meters deep. We didn't log it or anything, but we found a thin sequence of pelagics, and then we went back to the volcaniclastics again. But yes, within those pelagics, we saw little debris flows of basalt clast that had kind of rolled down the side. But a question we have is, how thick are those volcaniclastics? At what point do you get into more kind of typical ocean basement? Yeah. So there aren't too many papers on it. The only one I've read is by Ridd in 1970, and they suggest that the kind of source of the mud is at a depth of 3 kilometers, and then it's kind of appearing up from those depths. If you look at where the mud volcanoes are and the geological maps, they clearly are aligned along a fault. So I think that the fault is kind of guiding where the mud's coming up. But yeah, there's really been, I think the problem with New Zealand is there's so many cool things to focus on. This hasn't been particularly an area where people have really looked. Yeah, it's good.
Okay, so do you have any questions? You heard about the PhD, maybe some students.
Yes, definitely.
Can
Yep, please let us know.
get in contact with some of your work. So thank you very much.
Cool, thank you.
Rebecca.
Cheers, thanks.